Good morning. I should first say that it's a great pleasure for me to be here, to be invited to speak here. I'd like to thank the organizers for going into a lot of trouble to accommodate my rather complicated travel plans. I'm particularly happy to speak at this meeting in Brazil because I know that Brazil has a long and excellent history in statistical mechanics, and so it is really wonderful for me to be able to meet you, however briefly. Something went wrong, but I don't know what. You'll know the guy who sort of dropped off the screen here. This is Murphy's Law. I will talk about numerical calculations of granular entropy, but before I do that, I will talk, and in particular, this problem, how you actually count something that basically in practice cannot be counted. But before that, I will give a bit of a prehistory, which for this audience really is not necessary, but I'll do it all the same. And then so only part 3 of my talk is about granular entropy, which you could say is the entropy of sand. So let me go to the prehistory, because as you all know, the whole concept of entropy, of course, went back to the Industrial Revolution, in particular to this man, Sadi Carnot, who is really one of my heroes. Sadi Carnot, as you know, in the early 1820s, wrote an article on the maximum amount of work you could extract from heat. And although at that time he still had to accept, although he didn't believe it, that heat was a conserved quantity, he posed all the right questions. If only he had been able to follow his own intuition and not assume that heat was conserved, he probably would have invented all of thermodynamics. Sadi Carnot's article is simply brilliant. I recommend it to everybody. Anyway, he went only up to a certain point. He posed the questions. He explained how to approach the whole idea, introducing concepts of reversible engines and things like that. But then it took another 30 years, a bit more, before thermodynamics was formulated in the way that we now know it. And let's not go through all the laws of thermodynamics, but only the ones that are crucial for what I'm going to say now. Well, the first law is, in a sense, a law that is intuitively fairly obvious. It is that energy is conserved. It's obvious because you first define what energy is, and then you say, oh, it's conserved. But and then the second law, in its original formulation, is also a very simple law. It simply says heat doesn't spontaneously flow from cold to hot. Now, the point is that I know that many students, at least where I teach, really dislike thermodynamics intensely. So I would say that's about 90% of all students dislike thermodynamics. I know that in this audience that's different, but still the reason why people dislike thermodynamics is not because of this, that heat does not spontaneously flow from cold to hot, but what happened afterwards. Because what happened afterwards is that Clausius came along in the mid-1850s, and he just took this statement that heat doesn't flow from cold to hot and reformulated it into something that we now recognize as the second law of thermodynamics. He introduced a quantity that he called entropy, S in this, well, he didn't use S. And then he said, using simple arguments, it's actually not a very complex argument. He argued that in a closed system, during a spontaneous change, the entropy will never decrease. And so it's all very nice, and he introduced entropy, and that was the starting point for practical thermodynamics, because with that principle in place, other people like Gibbs could create a framework that allowed us to relate lots and lots of different experimental data. There was one problem. Clausius never told us what entropy was. And so we had this quantity that you could measure the change in entropy. You can use this formulation to say all kinds of things about processes that can and cannot happen. But Clausius avoided saying what entropy was. And so if you try to have a more microscopic picture of entropy, you have to move on in time. And the first person who is usually credited with having said something about the microscopic interpretation of entropy is this happy-looking person. It's Ludwig Boltzmann, and on his grave you see this statement that relates the entropy of a system to the logarithm of the number of states. So S is K log W. K is Boltzmann's constant because the units had been introduced before, so he couldn't just say it's S is log W. And this is what people usually say is the first microscopic interpretation of entropy. But there is a problem. And the problem is that, as you may know, Boltzmann committed suicide in 1906. And at the time when he died, actually quantum mechanics was barely emerging. Certainly, I mean, Planck was there, but nothing else had been written down. And so it is very strange how Boltzmann could have related the entropy to the logarithm of the number of states of a system, when at that time people really were thinking in terms of classical mechanics. You could discretize phase space if you wished, but counting states was not so obvious. And so the question is, how come that we have this text on Boltzmann's grave? I mean, how could he write this? And the answer is, he didn't. Actually, it was not Boltzmann who wrote down this expression first. The person who actually wrote it down is somebody else who is not totally unknown. It's called Max Planck. And in his famous article on the black body radiation, he wrote this: the entropy of a system with of n particles is K log W, there you have it, plus a constant. The constant actually depended on the number of particles. We'll come back to that at the end of the talk. But the main thing is that Planck said that in writing this expression, he was inspired by Boltzmann. So certainly Boltzmann was very influential in the emergence of this expression, but he was not the one to write it. Now, there is an unfortunate consequence of this fact that actually Planck wrote S is K log W, because of course at some point Planck also died in 1946, and if you look carefully on his grave, there's nothing. So I thought that we actually owe it to him to add something to his gravestone, so I thought maybe this would compensate for the absence of S is K log W. Good. Now the thing is, if you start from S is K log W, it tells you that, for instance, the entropy of this laser pointer is related to the logarithm of the number of quantum states, well, assuming that this is an isolated system, which it is not quite, of this laser pointer. But of course, I can't see the number of quantum states, so it is not something that gives you a lot of intuitive understanding of entropy. And so this is why when people discuss entropy in undergraduate textbooks or say on Wikipedia, they will use another more intuitive picture. And the picture that you will see, I have here a quote from Wikipedia, they say, entropy is commonly understood as a measure of disorder. And that's, people say, yeah, sure, because if you go spontaneously from an ordered state to a disordered state, you don't spontaneously go from disorder to order, so that is intuitively appealing. And very often it is even true, but it is not the second law. And so to explain that, I'll go back only 50 years in history, to 60 by now, to another problem that has to do with entropy and order, and that is the following phenomenon. If you go from a liquid to a solid, then clearly, if suppose that this is a closed system, so energy is constant, number of particles is constant, but if the density is high enough, then at some point spontaneously the liquid will go to a solid. And if you ask yourself how is this possible, then the normal explanation is, well, it is possible because actually as you go from the liquid to the solid, particles in the solid interact more strongly, they can release energy, and the energy released can heat up another part of the system so that on balance the entropy increases. And it is this energy release that enables you to have a transition from a disordered state to an ordered state. Now again, usually that is correct, but in the early 1940s, Elizabeth Monroe and John Kirkwood looked at this problem and said, sorry, it should even be possible to have a transition from liquid to solid, from disordered liquid to ordered crystal, if the system doesn't release entropy and energy. In particular, if you have a system of particles that's completely hard, so they cannot overlap, but they don't interact when they don't overlap, whatever way they're arranged in space, the potential energy is the same. If the temperature is constant, the kinetic energy is always the same, so there is no difference in energy between the crystal and the solid. No heat can be released upon freezing if you are at constant volume. And so you would think that as no heat can be released, they can't freeze, but Kirkwood and Monroe said, no, it can freeze. Now this was in the early 1950s, but it was something that was not easy to test, because as you know, atoms don't interact like hard spheres. And so it had to wait for another almost 20 years before people started looking at the problem. And the first studies of this kind of transition in systems of hard spheres were actually carried out in some of the very earliest computer simulations. These are the early computer simulations by Alder and Wainwright and Jacobson and Wood. And here you see a picture of Alder and Wainwright. This is Tom Wainwright here, who died a few years ago, or Bernie Alder, who is now, I think, 92. And they actually published a paper where they explained what happens if you take a system of hard spheres in a computer and look at what happens then if you... Wait, there's somebody else. Marianne Mansai. She is on the picture. She is not on the article. I know that you have a discussion about gender issues tonight. She was in the picture. She was not on the article. She was not totally unimportant for this work, because of the three, she was the only one who actually wrote the programs and ran the programs. And so at that time, it was apparently still common. I mean, by the way, she was not like an unskilled technician. She had a degree in mathematics. So she had all the qualifications to be on the paper. She wasn't. When Bernie Alder celebrated his 90th birthday, it was the first time I ever met Marianne Mansai. So he is here, together with Bernie Alder. You see Marianne Mansai. And so actually, I asked her, and she said that yes, indeed, she wrote the program, she ran the program. So something to discuss tonight, maybe. Right, anyway, so the main thing is that the outcome of the simulations of Alder and Wainwright and Marianne Mansai, although I should say that this bit of the simulation was already done before she was in the project, actually showed that as you increase the density of a system of hard spheres to a given point, that you have a spontaneous transition from the liquid to the crystal. And that is very curious, because it means that the liquid at this density has a higher entropy than the crystal. And that is, oh, sorry. Wait. Oh, sorry. Oh, you know, this always happens when I don't know how I get rid of this. I mean, good. Okay, no, I mean, he is always worried that I try to violate the second law. I don't. The thing is that actually, and there's since then been, there was work before by Monroe and Kirkwood, and there's been a lot of work since that actually shows that it's completely compatible with the second law. There is just nothing against this having a higher entropy than that at the same density. The main conclusion you can draw is that looking at order is not enough to determine which state has the higher entropy. Now actually this was in a sense already known before the computer simulations of the 1950s, because the first entropic ordering transition was actually described by the work of Lars Onsager, one of my other heroes, who showed that if you have a fluid of hard rod-like particles and you increase the density, that these particles spontaneously go to an orientationally ordered phase. It's not a crystal, it's a liquid crystal. It's actually the crystal that is in all the display screens on your computers, pneumatic liquid crystal. And this transition happens only because the entropy goes up at constant density. So it basically means that you lose orientational entropy, but you gain translational entropy, and that's what makes this tick. And then actually computer simulations subsequently showed that you can also get other phases, and all these phases, more ordered, they all form due to entropy. And in recent years there's been a whole zoo of these phases. Actually, these phases all have been observed. I'll show you now a few pictures from the work of Scher and Glotzer of phases that have not yet been observed. But the main thing is that if you take different shaped hard particles, you can reproduce a very large fraction of the simple crystal structures, the Bravais lattices that have been classified about a century ago. So you see here the that you can form cubic lattices, FCC, BCC, betadine, gamma brass. You can liquid crystals, pneumatic, smectic, columnar. You even get quasi-crystals, and this all has to do with the shape of the building blocks. So there is an amazing potential of making ordered phases by exploiting entropy. So it's the entropy increase that drives the formation of order, which is very counterintuitive, but that's something that we now understand a lot better. Now, that is my introduction about the normal kind of entropy that we learn from thermodynamics, and now I want to come to the granular entropy that is actually the core of what I want to tell. Now, the thing is that maybe I should start with a slightly historical background here. I attended a meeting in 1990. It was the first liquid matter conference in Europe. It was held in Lyon, in France. And the opening speech was given by Sir Sam Edwards, who has done a lot of work in theoretical physics. You know, the tube model for polymer solutions. He has been working on lots of different things, but at that time he was interested in powders. Later people have called that granular matter, and he commented quite correctly that because the particles in powder are relatively heavy, Brownian motion plays no role. So you can't apply standard statistical mechanics, the Gibbs style statistical mechanics to powder. And then he said, well, what you can do is you can define a quantity like temperature and a quantity like pressure by defining quantity entropy here, and then if whereas in normal thermodynamics you would say the temperature is dE ds, or normally you say actually ds dE is 1 over T, but you could say that. Here he says I have this quantity x, which he calls compactness, and later people called it compactivity, which is dV ds. Analogy was dt ds, but of course this cannot be the Boltzmann style entropy, and so he said the entropy here is a well-defined quantity. It is the logarithm of the number of ways in which the grains can be assembled to fill a volume V. Now, what I should say then is that I was listening to the talk, I came to listening to this statement, and after that I can't remember a word, because I always thought, why? Why is he saying that? Because basically what he was doing is to make a kind of microcanonical assumption about the number of ways in which you can pack particles in a volume. Because as you know, in statistical mechanics, you say S is k log W, and the underlying assumption is that all the different states of the system are equally likely to be occupied if you're at constant energy. Here he made the assumption that all packings of a granular medium are equally likely to be occupied, and I just couldn't understand it, so I don't know what he said in the rest of the talk. Well, actually I could read it in this paper. Anyway, the thing is that this entropy may be well defined, but it's very hard to make any statements about the validity of the Edwards theory if you actually cannot compute this granular entropy. And so this was really an issue, because whatever the number of ways is that you can pack particles in a volume, it goes up very, very rapidly, at least exponentially, with the number of particles in the system. So actually brute force counting, and I'll come back to that in a minute, is not going to work. At least it's not going to work for any systems that are even remotely approaching the thermodynamic limit. So this was a real issue. Now I'll make a slight detour and say a bit about the kind of structures that form if you make these random granular packings. And it has a long prehistory, and I'll skip actually most of the prehistory and focus on first a bit on the work of J.D. Bernal. I don't know how much you know about Bernal. Bernal was a he was among his colleagues and even outside his immediate circle of colleagues, he was called a sage because he knew everything. So not just physics, he was also a Marxist, he also knew about history, he knew, I think, at some point somebody asked him, is there anything you don't know about history? And he said, well, yes, I think I'm not so well aware of the history of Bulgaria in the 3rd century AD. Okay, right. That was Bernal. And actually, he was the person who did the first protein crystallography. So he said that's the way to get the structure of proteins. He could do the crystallography, but he couldn't yet analyze the data. His students did, and 4 of them got the Nobel Prize for that work. So, I mean, there's much more to say about Bernal, but I won't. Later in his life, he got interested in the structure of liquids, and he made mechanical models of liquids. And he did that by taking the steel spheres inside ball bearings and then putting them inside basically the inside of a soccer ball, so a rubber balloon, and then adding paint to this balloon, and then draining the paint, but wherever 2 particles were touching, due to the capillary forces, the paint would stick, you would let it dry, and then you had a clump like this. Now, of course, why was it in rubber? Because if you don't do it in rubber, but on a hard surface, you see it actually forms a crystal. So he had this in the rubber, and then he took the sphere apart, and he started counting the number of contacts for every particle. And he could, by the way, he didn't do that himself. There was always an assistant or 2 who did actually counting. So in his case, in the article, he will say, I thank Miss Wilkinson for counting the 733 different environments that you find in this packing. But anyway, so he analyzed these packings, and at some point it became so tedious that they started to use a computer to do the analysis, and then they thought we might as well use a computer to make the packings. But the main thing is that while doing this, he made a statement about the nature of this packing. And what he said is the following. This is actually a younger Bernal, this before he actually could have said it. He said that it seems that the fraction of space occupied by the spheres, if you randomly pour them into a container, is about 64%. And that's different from, as you know, the Kepler packing, pi over square root of 18, which is 74%, a bit over. So he observed this in his packing experiments, and then he said, this number must be mathematically determinable, but as far as we know, undetermined. And that really is a serious understatement. It is still undetermined, and it's not even obvious that it is quite as well defined as Bernal thought it was. So that may be the reason why there are other things that may be better defined that you can determine, but even there, analytical results are very few. What?
Do you believe it's well defined?
No, I don't believe that this is well defined. But it certainly stimulated a lot of work. Now, this is for spheres, but if you go away from spheres, it becomes the situation changes because spheres can be the maximum density that you get. The regular packing is 74.05% of space, random packing 64%, and there was work by Paul Chaikin, Alex Donoff, and Sal Torquato, who were looking at the packing of M&Ms, these oblate ellipsoidal particles, and they were looking at what is the maximum density of packing there. And it turns out that the maximum density of packing, as soon as you go away from a sphere, so this is a sphere, this is a prolate or lucid, this is oblate, the maximum density of random packing goes up. It is higher than for spheres. It is a bit like what Ulam conjectured about regular packings, that actually the spheres in this case, that spheres are the least efficient and other shapes are more efficient, but here you see the random equivalent. This is the M&M experiments, it's very noisy. The rest is computer simulations. But the main thing you see is that if you take ellipsoids, you can pack a higher fraction of space. If you take biaxial ellipsoids, then the volume fraction that you get is almost 74%. So it's almost as much as you can get for spheres in regular packing. So you really can pack more densely. And so this is actually for an aspect ratio between the axis of 1.3 to 1.3. So it is a not completely obvious number, this optimal packing fraction. Now, the thing is that, of course, if you look at M&Ms, it is actually fairly strange that they should have taken this shape. Because if you take spherical sweets, they fill less of the volume of the container. And as you know, one of the essence of selling things is to get as little in the box as possible. And so M&M is a signal failure there. They got too much in the box. But sometimes in industry, there are problems where you want to get as much in the container as possible. So my question is really, if ellipsoids are packing more densely than spheres, was this already known? So I know that the first article in Science, sure enough, was by Daan Frenkel and Chaiken, but maybe people already realized it beforehand. So where would you need this? And I thought about this, and I thought, well, in the mid-19th century and later, when there were steamships, they would have to get coal. Later it was oil, but initially it was just coal. They would have to get coal on board. And of course, if you put coal in the hold of a ship, you want as much as possible, but you're not going to just impose the Kepler packing. So you're not going to put it there hand by hand. Just pour it in. And you want as much as possible. Now, of course, if you have natural coal, the shape is what it is. But then, in the mid-19th century, people developed the production of coke, this compressed coal dust, and you can compress it in any shape you like. And so they started to make egg coke. And I thought, would the shape of egg coke maybe have to do something with the maximum density of packing? So then you go to Wikipedia, and here you see egg coke. And these are the numbers for the different sizes of egg coke. And then you can say, how does it compare to this? Where is egg coke on this picture? Well, clearly it's somewhat prolate, but where are we? And the answer is here. So, although I have not been able to find back the relevant patent literature from the 19th century, it is clear that by trial and error, the engineers already knew this answer. Good. Now I come to the actual problem, I go back to the problem of granular entropy. So if you, in order to count this, what people had been doing before is actually to prepare different packings. So you take, say, 12 particles, you put them in a container. Usually this is actually simulation, but you put them in a container such a way that they don't overlap and that they are jammed so that particles cannot move. And you do it again and again and again. And then you just count how many times, how many different structures you'll find. And at some point you find they can start producing the same structures, and that means that you know that you're approaching a point where you have enumerated them all. The only thing is that this works for a small number of particles, 10, 12, 14, maybe a bit more, but certainly not for larger. So what we did is to generalize the problem first a bit by, instead of taking totally hard particles, we took particles that are slightly repulsive. So, and the reason for taking particles that are slightly repulsive is that if you do that, then the potential energy of the system is defined for all possible positions, not just, so it's not just, because for hard particles it's either 0 or infinity. If you have soft particles, then for any configuration you can define a potential energy. So that means that you can define a potential energy landscape, and as the particles move in this energy landscape, they can either be away from a minimum or at a minimum. And so what you see here is a very schematic drawing of a dn-dimensional potential energy landscape. Now my drawing skills are very limited, so I have to stop at 2. But you should see this picture as follows. This is a particular stable packing. That means that all particles are, so the potential energy is a minimum, the Hessian is always positive, so whichever way you try to displace a particle, the potential energy goes up. Away from this point, you're not at the minimum, and if you, for instance, start here at this point with the system, and you minimize, then you end up here. If you start here, you end up there, but if you start here, you end up here. So it basically means that every minimum is surrounded by its basin of attraction. And if the minimization that you use is steepest descent, then it also means that all these basins of attraction are compact. So that is one thing, you have these compact basins of attraction surrounding the different minima. And the second thing that is important is that the total configuration space, so here I assume actually that, well, I mean, I've just drawn here a configuration space quite schematically, but the main thing is that in principle, every point in this configuration space belongs to a basin of attraction, because you take the particle, the system, you minimize and you end up somewhere. So every point must belong to a basin of attraction. And so it means that these volumes, they tile the total space available. Now that's the only thing we use. Now, so then the question is, can we obtain the total number of minima numerically? And as I said, the standard approach was the brute force method. We just say, I take a random number of, a large number of random initial configurations. So you take the particle positions totally at random, like in an ideal gas. Of course, typically the potential energy will be very high. You minimize, you find the minimum. You take another random initial condition. You minimize, you find another minimum. And if you go on long enough, you just keep on counting how often you visit different places. And then the second method that I'll explain is what we used, which is the average volume route. And I'll explain how this works. But first, how does the random method work? And I use a human example to explain it. Suppose that you're staying, you're looking at a hotel, one of those big buildings that is typically you find in a Hilton or so, a rectangular block. So you can measure the volume by looking at the outside of the hotel. And but that only becomes important later on. Now assume that I have no idea how many rooms there are. The strategy of random sampling is the following, that you say, you go into the hotel just the day it opens, and you say, I'd like to work here as a receptionist. And people say, fine. And you go and sit there. And as you know, in the reception of modern hotels, you just can code a magnetic card. So the first guests come in, you give them a room number randomly. They go away happy, you go to the room. The next person comes in, you give them a room number randomly. But the important thing is the number is random. It might be the same. It's very unlikely if it's a big hotel, but it might be the same. At a certain point, angry guests start coming down to the reception again and say, there's already somebody in my room. That means that at that point, you're starting to sample a sizable fraction of the total number of rooms. And if you were to continue, eventually, you would have covered all possible rooms. So the main thing is that this random sampling is something where you just wait to see if you see duplicates appearing. So that's the random method, but it doesn't work very well. If you work, well, in a hotel it would work. You would be fired before you could complete the experiment. It would work. But for granular media, it's hopeless because the total number of rooms, the total number of basins of attraction can be so huge. Therefore, the other route that you can follow, and that's the average volume route, is that instead of working in the reception, you walk in and you say, give me any room. And assuming that, again, there's enough space in the hotel, they give you a room. You go in, and then you actually have a ruler with you, so you see here. And you actually measure the width of the room, the breadth, and the height, and you know the volume. Assume that they're just simple rectangular rooms. It's a pretty good approximation. And then you go down to the reception and say, actually, I want another room. Give me another room at random. And so you go on, and you can then determine the average volume of the rooms. And if you know the average volume of the room, and you know the volume of the hotel, because you could see from the outside that it's just like a shoebox, then you know the number of rooms. And that's the trick that we use. So here, I explain now how it works for us. Here again, you have these basins of attraction of the different minima in configuration space. And then what you can do with simulation is to actually compute the volume of a given basin. So you say, I prepare a system in random, I minimize, I'm here. And now what you can do, and I will not go into the technical details there, but it is standard simulation techniques. You can compute the volume of this basin. And then you prepare another state, you compute the volume of this basin, etc. And so you can sample basin volumes. And so this is what you can do. And the important thing is that I said these basins, they tile the total space. So the total space is just the system size, or here I wrote 1, but it's the size of the system to dimensionality times the number of particles, and that must be completely filled by all these basin volumes. And that basically means that you can multiply by omega, the total number of volumes, and you divide, and then you get that the sum is just omega times the average. So if you compute the average basin size, you have the total number, because the number is then this volume, which is trivial. This is the number you've sampled, and this is what you want to know. Now, I must say that I take a few shortcuts. I don't explain some of the technical problems involved that Took us 6 years, but okay, that's something else. But this is basically the way we were able to approach it. And the key thing is that what we've done is to go away from the brute force sampling, which is a counting problem, to a sampling problem, because we don't need trillions of different samples to get this. We only need a few thousand. I mean, of course, the more the better, but it has become a sampling problem and therefore it's tractable. Now, once we have this technique, we can start asking questions about Sam Edwards granular entropy. And so one of the first things that we looked at is whether indeed you can associate an extensive entropy with the log of the number of states. And this is something that is important because, whoa, okay, I think so, yes. Because the one thing you really want of thermodynamic quantities like entropy is that they're extensive. That means that if you double the system size, you want to double the entropy. Otherwise, it is very difficult to introduce meaningful relations where you can compare entropy per particle in different systems. And so this is something that we could compute. Here you see at this point, we could go up to 128 particles with the techniques that we have now, which are not different but just more efficient. We can go beyond that, although we have been so busy looking at say, low-hanging fruit that we haven't done much beyond this, because it's just, yes, you can do it, but it takes a lot of time. And you see that the entropy does increase quite rapidly with the number of particles. See here, S is the log of omega. So if you look at this point, that is the log of omega is almost 600, and this is the natural log. So it means that you talk about 10 to the power 250 states. Now, clearly, that is not something you can compute by direct enumeration. So it was essential to use this average volume sampling trick to get it. Because if you compare it with direct enumeration, this is about 10 to the 10 times faster, 10 to the 240 times faster than the existing method. So it really makes a huge difference. And here you can see that an algorithm sometimes allows you to do something that computer power alone will not allow you to do in the foreseeable future, and I would say beyond. Okay, so that's the first thing. So that you see that you can get really large numbers of distinct packings. The other thing that we found, and here I have to say something, is that if you take such an overcompressed system, so basically what we take is a system where all particles, or the system goes to a minimum, and this is easiest to achieve if you're not exactly at the point where the system just reaches jamming, but you compress it a bit so that the potential energy goes up, but then every different state is clearly at the different potential energy minimum. And what we found is that actually the volumes, these basin volumes, are not all the same size. Which is not, I mean, as you remember, Sam Edwards assumed that if you have a jammed structure, that every packing is equally likely. That is in principle not what we found for these dense systems. In fact, we found that different systems give you different packings have different probabilities. But that's again no problem, because then instead of using the Boltzmann expression for entropy, we use the Gibbs expression. And so if this is the probability to find the system in a certain basin that is proportional to the volume of that basin, we can compute these things actually directly from the simulation. And this expression, the Gibbs-like expression, is actually more accurate than the Boltzmann expression, because the Boltzmann expression needs some additional analysis to compute. To say in a few words, why do you need additional analysis? Because I said you randomly generate minima in the system. But actually, a minimum with a large basin of attraction is formed more often than a basin with a small minimum basin of attraction. And so, in the Boltzmann case, you have to correct for the probability that you sample a large or a small minimum. It so turns out that if you do the Gibbs definition, this expression completely, exactly cancels out this bias, and so the Gibbs expression is precisely what you sample. So that's very fortunate. So this is easy to compute reliably. So then you can look, now here you see the Gibbs expression, it looks actually very similar, even the numbers are not that different. So there's not a huge difference between Boltzmann and Gibbs here, but there is an issue. And the issue is that I said, if you want the thing to be a decent entropy, it has to be extensive, so it should basically go through the origin. It should be linear, but the main thing is it should go to the origin. And you can say, oh, it's not so bad, but this is really not what we were very happy about. And so, I don't know, I assume that in your work you also have group meetings, and this is the kind of thing where on a very, in an informal way, you can discuss things with students and postdocs, and that's also what we do. So here you see a very democratic discussion. And here the two, Fabien Pausson, the postdoc, and Daniel Asenjo were working on the problem at the time. And I was looking at the picture and I said, well, this is not very linear, is it? And what do we do about it? How can we treat this? And I said, well, let's subtract log n factorial. Actually, just divide the number of packings by n factorial. And then immediately Daniel and Fabien said, well, wait a minute, these are polydispersed particles. I didn't tell that not all spheres are the same size, they are different size. The reason why we take different sizes is because if you take a small system and particles have all the same size, then they are very likely to crystallize. With polydispersed system that doesn't happen, but it means that they're all different. So this you can't do. Now, it was a democratic group meeting, but there's always a limit, and say, okay, try anyway, good. If you do that, then actually there's more to it that's in this paper, but then what you see is immediately the numbers become less because you've subtracted log n factorial. The data, we now also have 3D data that are better, not because the 3D is, yes, 3D is easier, but because it was done more recently, and you see that now we get straight lines that are completely compatible with the assumption that this entropy is extensive. Now, this is important, so you can get an entropy. I said for overcompressed systems, different basins are not equally likely to be populated. But what happens if you go to unjamming? So actually, exactly the point where the system first touches. This is what happens if you pour spheres in a container. And this is more recent work by Stefano Martignani, who showed that the entropy as a function of volume fraction, actually, there's two entropies, the Gibbs entropy and the Boltzmann entropy, and they're only the same if all packings are equally likely. You see here they're different, and they seem to get to a point where they're all equally likely, and this red line is the jamming transition. So it seems, this strongly suggests that actually at jamming, all packings are equally likely. And that, of course, was something that Sam Atras apparently intuitively understood. I still don't understand how he got to this idea, but this certainly seems to be compatible with the analysis that we have now. I have to, in the last few minutes, do one quick thing, because this dividing by n factorial seems strange. So we have to go back to this important person, Gibbs, J. Willard Gibbs, from the Gibbs paradox. And you all remember what people say about the Gibbs paradox. So you go to the textbooks, and they say, well, basically, they all say quantum mechanics, quantum mechanics, quantum mechanics. The indistinguishability of the particles, this is the key point. Then this is, I would say, all the textbooks is not quite true. Because, for instance, Nico van Kampen, in one of his famous polemical articles, say, I take exception with that statement that it's not possible to understand classically, and it can be derived by logic rather than by the somewhat mystical arguments of Gibbs and Planck. He doesn't take any prisoners, does he? Even better is James, who talks about Gibbs' style, and he says it's usually sufficiently clear, using no more than twice as many words that Gibbs or Einstein would have used to say the same thing. So that's the definition of clarity. If you can reach that, you're okay. But occasionally he says, and this is the sentence about the Gibbs paradox, and it's totally incomprehensible. He said, again, when such glasses have been mixed, there is no more impossibility of the separation of two kinds of molecules in virtue of their ordinary motion in the gaseous mass without any special external influence than there is of the separation of homogeneous gas in the same two parts in which it has one be divided after these two have once been mixed. Yes? Okay. Right. So I did the experiment. Maybe I'll just show one bit of the movie, because I mean I usually don't do experiments. I'm not sure whether actually I don't think. Basically, I tried to compute this the change in entropy in a glass of milk, and I concluded there was actually no change at all. Right. So the main thing I want to show is that it is really true that even if you have particles that are different, and I will in view of the time not go through the argument in any detail, that although the partition function is the log of the partition function is not extensive. if you look at two systems and you look at the number of ways in which you can distribute the particles without changing the macro state, that actually you get something where immediately this comes out. So that actually what you have to look at is the partition function divided by n factorial even for polydispersed particles. And so this had immediately consequences because there was this thing in the Wiener Zeitung, deranged scientist defaces Boltzmann grave, and you see here what happens. Basically, if you don't care to distinguish the particles, then that's the answer. And of course, this is a good point to stop, and I thank you very much for your attention.
Questions?
I would like to talk about this n factorial. I think that when we say that entropy is related to the number of states, we have to know what's the meaning of state.
Exactly.
In my opinion, the meaning of states must be given only by the quantum mechanics. In classical mechanics, the state is not well defined. If you say that it's a point on a phase space, then it's impossible to count the number of states.
Yeah.
So if you go to quantum mechanics, and then you get your n factorial. And if you want to do classical mechanics, you just have to take the limit. Okay.
Yes and no. I mean, so I agree. You have to go to quantum mechanics. The example that I showed, where I didn't have time to explain, is that I take a set of particles that are different. I think of say colloidal particles that are sufficiently large that they're all different, but I assume that I make an infinitely dilute suspension in space, which of course you don't do with colloids, but it's a thought experiment. Because it's infinite dilute and the particles therefore don't interact, you can use the quantum mechanical ideal gas expression for the partition function. You take the logarithm of that thing and it is not extensive. So even there, the quantum expression has this strange, and of course if the quantum particles are really, like if you have helium-4 atoms, sure. There's one, I mean, any permutation doesn't change the state of the system except for a phase vector. But even in the case of distinct quantum particles in the ideal gas limit, you have to still divide log or the omega by n factorial to get something where you have the system invariant under any permutation that leaves the macroscopic state unchanged. So it is a bit more subtle, but on the whole I agree with your argument.
I have a question here. Well, in my view, I think that extensivity is something that applies when you have a very large number of particles.
Yes.
Even when you have a finite systems, I mean, you are not obliged to have extensivity.
Absolutely. I mean, this is always the thing that in computer simulations, you have to ask yourself the question, when is large enough? And so the fact that in a very small system you see deviations from the finite, the infinite size system behavior is something that you should not necessarily be worried about. The only thing is that here, because the behavior otherwise looked quite regular, we were concerned that it really was hiding something more serious than that. But on the whole, I agree that you shouldn't take the results for small systems as indicative necessarily of infinite systems.
No more questions? Just a final comment. This picture, I know it's from the Onion.
Yes, it is.
Yeah, but that could be in Brazil in these times.
I think that actually it could even be in the US in this time, or even a bit more.
Here the situation
I think
now
it's official policy, isn't it?
Yeah, that situation here is getting worse. We can talk.
I mean, that would be a separate talk. Let's.
So let's thank Professor Frank again.